Okay, we're going to use the properties of Fourier series to prove this result. This is one of many series where the pi can be expressed as an infinite series. So this is an interesting result that I'm going to prove. But the first thing I'm going to do is look at the basis of Fourier series. So this is a function, which is any periodic function. It need not be continuous, so certain types of discontinuities are allowed. But the main condition is this function must be periodic. And in this case, my period is going to be 2 pi, because the reason I'm choosing 2 pi is because it's the period of any sine or cosine, simple sine or cosine graph. So that's the reason why I choose 2 pi as the period. And if the period is 2 pi, you can write a Fourier series like this. If we have a look at it, you can see in essence how it works. We have we have a sine series and a cosine series. So basically we're writing out this particular section of a curve or a graph as an infinite series of sines and cosines. The cosine is multiplied by this coefficient, which depends on n. When n equals 1, obviously this is just a normal cosine graph, which has a period of 2 pi. When n equals 2, the period is obviously pi, because when you do the graph y equals cosine of 2x, it has a period of pi, because it's twice as many oscillations in a given distance. This is basically what's happening, and the same with the sine series. So you can see why I'm writing it as nx. So I'm basically adding lots of different sinusoidal curves which have periods that are 1 times as much as a cosine graph, 2 times as much, 3 times as much, like that. You can also think of it like overtones on a string instrument, or oscillations, if you want to think about it in a physical sense. And this term here is my sort of A naught or B naught type coefficient. So this is my n equals 0 type coefficient here. So each coefficient multiplies by your cosine or your sine series, your sine term. It's fairly simple. Now, this may seem fairly abstract, but this can be used to prove pi as a series, and it depends. It's done by choosing a particular value of f of x. In essence, what I'm going to do is I'm going to evaluate this function at a particular point. In fact, in this case, I'm going to use 0, which is going to remove this particular series, because obviously sine of 0 is 0, and just leave me with this series here. Now, I'm going to basically say 0 is equal to this thing here, and if my A naught is in terms of pi, then I hopefully should be able to get an infinite series in terms of pi. That's basically what my aim result is going to be. So now I need to define my function. This is the function I'm going to define, partly because it's simple, and also because I know it works. It gives the result I want. So my function is defined as x from 0 to pi, and 0 from minus pi to 0, like this. And I should point out that this is only one section of the graph. This will go on forever, so after pi it goes back to here and then up like that. This basically basically has a period of 2 pi. And my Fourier series, if I was to express this graph as a Fourier series, every time I increased n, every time I added a further value of n, then my sines and cosines would start to approximate this curve more and more. And funny things would happen at the discontinuity points, where, for example, funny things would happen at pi, but I'm not going to really go into that. I'm more interested in proving the result that I just said. Okay, so now I know. So now I've basically given a quick introduction to where I'm going with this, and now I'm going to sort of do the mathematics, the heavy algebra, in order to prove this. The first thing, obviously, I need to do is work out what my coefficients are actually going to be. So I can come up with this. So I'm going to work out what my A naught coefficient is first. In order to work out what my A naught coefficient is, I can integrate between pi and minus pi, which is obviously over my entire period, and f of x. So I'm integrating both sides of this equation, basically. So I've integrated my A naught over 2 dx, and I'm integrating these. But the important point I should make up here is the integral of these two terms here is going to be 0, because I'm integrating a cosine and a sine graph over its entire period. So there's going to be a positive area and a negative area if you think about it geometrically. So these two terms are going to be 0. So I'm just left with my integral of pi to minus pi of x dx is equal to a0 over 2 dx. This can obviously you can look at the graph to work out what the integral is by looking at an area, and it's quite clear that you don't need to worry about what goes on here because the integral of that's going to be 0. So if I just look at the area under this part, you can see that the integral of x between pi and 0 is x squared over 2 evaluated between pi and 0, and that's equal to a0 x over 2 evaluated between pi and minus pi into this integration here. So I've just done a basic integration. Evaluated that, you get this, which basically says that a0 is equal to pi over 2. So I've worked out what a0 is. Now I'm going to work out what an is, which is significantly harder and takes significantly longer. This is just a bit of how to work in order to work out what an is. It's some things about functions. If you wanted to integrate between pi and minus pi, or it could be another period, but in this case it's pi and minus pi, cos mx, cos mx, where m and n may or may not be the same. And this can be described in terms of a piecewise function. It's 0 if m is not the same as n, and it's pi if m equals n. And this is another way of writing it, although I wouldn't worry too much about this. I'm basically going to prove this, and this will turn out to be very useful in working out the AM coefficients. Okay, so the proof of this is quite simple. It just uses some basic trigonometry. So I'm going to come up with my my addition formula for expanding cosine, which is here, which is fairly straightforward. So what I'm going to do is think about the case where m is not equal to n. So I'm just integrating this as usual. I can re-express this cosine mx and cosine nx using this identity here. I can let mx equal a and nx equal b. So you notice that if I add cos a plus b to cos a minus b, the minus sin a sin b cancels with the plus sin a sin b, and you get 2 cos a cos b. So obviously that's where the half comes from, because we want 1 cos a cos b, obviously. So that's basically what I've done. I've just used this identity to rewrite the integral like this. Okay, now applying the integration, basically I put the integral in front of each term, so that's all I've done there. And then just simply evaluate the integral. The cosine obviously integrates to make the sine, and then this factor of m plus n drops out. That's just integration by recognition. The same thing happens with the other term. So like this. Now, if we evaluate this sine of so basically we're putting in sine of pi plus sine of m pi plus sine of n pi. So we've got m plus n times prime. So basically, a multiple of pi here, which is 0. In this, sine of pi is going to be any sine of anything multiplied by pi is going to be 0. That's fairly straightforward. And the same goes for this part here. We've got n minus n, so sine of an integer multiple of pi. Again, it's going to be 0. And the same thing will happen when you evaluate it at the other limit. The sine of minus pi is also going to be equal to 0. So you can see very quickly that this is equal to 0 if m and n are not the same. If m and n are the same, we've got to do this reasoning again, because obviously if m equals n, then we've got a 0 on the denominator, which is not very good. So we've got to go back to first principles when m equals n. So m equals n here. So obviously I can replace m with n, and I've simply got an integral of cosine squared mx dx. To evaluate this integral, again we need to use this addition formula. But in this case we let b equals a. So cos 2a equals cos squared a minus sine squared a, which is proved using this. I'm going to use the Pythagorean identity, sine squared a plus cosine a equals 1. And we can simply use this to rewrite the minus sine squared. So that's 1 minus cosine squared, obviously. So in essence, we can rewrite cos squared mx dx as cos 2mx plus 1 over 2. And you can see this because cos 2a plus 1, so you're adding the sine squared to this, so the sines cancel out. And you get 2 cos squared, so you need to divide by 2 here. So I basically let a equal mx. That's what I've done here. So I've just redefined. So I've done a little substitution into my integral there. Very straightforward. So again, I split up the integral like this. So when you integrate this term, again, you get the cosine becomes the sine, and we have to evaluate it between pi and minus pi. Again, we're multiplying. We're doing sine of an integer multiplied by pi. So, like before, this is going to be 0. So we just need to look at this term. So we've got to integrate 1 over 2 dx, which is obviously x over 2, between pi and minus pi. Pi over 2 minus pi over 2 pi. This thing here is another very useful identity that I will need, and which I will not prove here. But the proof is very simple. You're just using trigonometric identities like this. You might want to use the sine addition rule as well. So this is not difficult to prove, but I'm not going to waste time doing it. Okay. So now we're doing all the preparatory work to find the AN coefficients. So again, we need to keep referring back to this basic function. So I'm going to use the properties in the preparatory work to find the AN coefficient. So this is basically what I'm going to do is I'm going to multiply everything by cosine, and then I'm going to integrate. So you see here basically what happens. The A naught over 2 multiplied by cosine integrated, that's fine. And I'm integrating this and then this. The first thing I'm going to point out is what happens to the sine series. Now, it doesn't matter whether m equals n or whether m and n are the same, whether they don't equal or whatever. This is always going to be 0, which is basically using this thing here, which I didn't prove. But that's always equal to 0, so we can just ignore this term here. This one here is 0 if n does not equal m, which I actually proved. And if m equals m, it's equal to pi. Here we go. It's equal to pi. Again, it's something I also proved. It's cosine squared, integrating that's equal to pi. Now, a quick word about the sum. Since we're looking at n equals m, we're only looking at the case where n equals m, so we can just take out the sum, because when n doesn't equal m, obviously that's going to be 0, as I showed before. So we can remove the sum in the case that n equals m. So, the integral of fx cos mx dx is basically just equal to this a naught over 2 cos m dx plus this a naught cos squared mx dx, which is what we did earlier in the case that m equals n. You can see here I'm evaluating the right hand side of this equation, so series type bit is what I'm evaluating at the moment. Okay, you do this integration again. This cosine becomes sine over 2m, and you should realise by now that when we have a sine that we have to evaluate between these things, that just disappears. So we end up with the AN pi, and you can see, and the AN pi comes from again the preparatory work, where I demonstrated that the integral of cosine squared here is equal to pi. So obviously we've got an AN in the integral, so that's going to be AN pi. Okay, so that's the right hand side evaluated. Now I need to evaluate the left hand side, which is this integral directly, fx cos mx dx. So we need to split this up into what fx is. We know that it's 0 multiplied. Obviously I've got a multiply by cos in here, but that's just 0 between the minus pi and the 0. Actually, that should be 0 on the top term and minus pi on the bottom term, but it doesn't matter if it's 0 anyway. Plus my pi to 0 of x cos mx dx, and the x comes from the original definition of the function here. So I defined it as being I defined x equals x in this bit here. So again, there's nothing particularly difficult about that. So I've just basically got rid of this term, and basically to evaluate the left hand side, I'm integrating x cos x and x dx. Again, this can be done with integration by parts. So this is the formula I will use. It's very easy to do. It's just integrating the product basically. I'm not going to prove this in this video, but I can do it another time. Very simple. So what I need to do is I need to define my variables. I'm going to let u equal x because x is becoming simpler. So du dx is going to equal 1 in this case. Okay, so my u is going to be equal to my x. My dv dx is going to be my cos mx dx. So to work out what my v is, I just need to integrate cos mx dx, and then I get sin x over there. So therefore, using this equation here and what I've defined as my variables, the integral of x cos x mx dx is equal to uv, which is x, multiplied by my v, which I worked out as sin mx over m, so that's where that comes from. Of course, I'm going to keep my limits here, minus the integral of v, which was again the sin mx thing over m, multiplied by du dx, which of course is 1. Okay, so I've done this. Again, this one, when evaluated between pi and 0, this thing disappears as usual. Nothing to worry about there. So it's just this thing I've got to worry about now. The plus sign here comes from the fact that when you integrate sine, you get a minus cosine. So the two minuses conveniently cancel out. So that's the plus. Anyway, apart from that, the sine becomes cosine, and a factor of n drops out as it does so. So we get an m squared on the bottom here, and that's evaluated between pi and 0 as usual. So, in order to express this conveniently, we know about the function cos mx. Any integer multiple of cosine x, cosine 1x, cosine 2x, whatever, is always going to be minus 1 or 1. And if you look at the cosine graph, the odd multiples are always equal to minus 1, so cosine of x is equal to minus 1. And the even multiples are always equal to plus 1. So cosine 2x is equal to plus 1. Or indeed cosine of 0 is equal to plus 1. The easiest way to express this is minus 1 to the n. Because minus 1 to the 1 also equals minus 1. Minus 1 to any even number also equals 1. So we can express the top term, thing, as minus 1 to the m, obviously over the m squared. And then substituting 0 into here, we get cos of 0, which is 1, minus 1 over m squared. And all I've done here is factorised it. So therefore, 1 over m squared multiplied by this is equal to an pi. And the an pi comes from the right-hand side of the equation, which I evaluated. Remember, all I've done, taking you back to the original equation, is I've integrated this and multiplied it through by cosine mx. So this is the left-hand side, which I've just done now, and then this bit's obviously the right-hand side, which I also evaluated. The right-hand side, as I showed you, evaluated to an pi, and the left-hand side is this thing here. So obviously now we have an, which is equal to this thing. Now, if I was to write a proper Fourier series, I would also need to work out my Bn terms. But I'm not going to bother doing that, because it's not needed. As I explained right at the beginning, we're going to be evaluating this at x equals 0. So we don't really need to know what the Bn is, because the sign is just going to disappear anyway. But if you wanted to write out a Fourier series for this repeating function, you would need to know what the n is. So that's a possible exercise. You can do that at your leisure if you're particularly bored. But for this proof, it's not necessary. So what I've done, written out the Fourier series again. I substituted my a in here and my a0, which is pi over 2. So I substituted that in. But obviously I haven't evaluated the bn. You can do that at your leisure. Okay, that's basically all sorted out. I don't know why. I think I've written this twice. I don't know why I've written it twice, but I haven't really written it twice. Okay, this is the Fourier expansion that I wanted to get. Okay, so now all I need to do is prove the result, which is very simple to do. I'm only going to evaluate my original function at 0. And as you can see, if we go right back to the beginning, the value of f at 0 is 0. It's 0 here. So we can safely say that f of 0 is 0. Also, anyone knows that sin of 0 is also 0. So substituting this in to my Fourier expansion, f of 0, the f of x, is going to be equal to 0 here. So that equals pi over 4 plus this thing multiplied by cos of 0, which is 1, so we can just leave that out, plus this thing here. And sine of 0 is 0, so we can just completely ignore this, which is very convenient because it means I don't have to spend ages working out what bn is. Okay, so now we've basically done it. All we need to do now is a bit of convenient algebraic rearrangement. Take pi squared, well, take this sum onto the other side, That's all I've done here. Actually, I'll explain thoroughly how I've managed to come to this. So I've taken this onto the other side, and then I've put the factor of 4, well, in this case minus 4, into here. So take it onto the other side to make it negative. Okay, yes. What I've also done here is I've taken the pi out. So, okay, to get from this stage to this stage, I've multiplied through by pi. 0 times pi is obviously 0. This times pi is the pi squared, and then that removes the pi on the bottom here. You can take it out something like that. So that's what I've done to get the pi squared. And then taking this onto the other side, which hence the minus sign, and then multiply by through by 4 to get this, and then taking the square root to get 5. Just simple algebraic rearrangement. So that equals that. What I've done here is I've got rid of the minus sign because I don't like it. To get rid of the minus sign, I've just replaced minus 1 to the n with minus 1 to the n plus 1, which is something you can do. So I've just changed all the negative ones to the positives, and all the positive ones to the negatives. But obviously minus 1 times minus 1 becomes plus 1. So again, very simple there. Okay, this bit's a little bit tricky conceptually, but I've defined my n in terms of a new variable, 2k plus 1, and k can take any of the natural numbers, 0, 1, 2, whatever. And the reason I've done this is because if you go through and evaluate this bracket here, if n is odd, then this becomes even. This becomes 1. So 1 plus 1 is 2, so you get an answer. However, if n is even, say 2, 2 plus 1 is 3, minus 1 to the power of 3 is minus 1, this becomes 0. So whenever n is even, this particular version of n becomes 0. So we can sort of ignore these terms and come up with a more general result. So I've left n equals 2k plus 1, because for any k, n will always be odd, because this is the equation for an odd number. K can be 0, 1, 2, or anything, and then it'll always be odd. So I can replace this with simply 8, because this is always going to be 2, because like I've said, when k is odd, this becomes 2, and when k is even, it disappears. So it becomes 0, so I've taken that out. So this becomes 8, because 4 times 2 is 8. And then the bottom term is even easier to understand. That's just my substitution, n equals 2k plus 1, so I just substituted that into there, squared like that. So here is my result, which I have proved. Pi equals square root, sum from k to 0 to infinity, of 8 over 2k plus 1 squared, which is square root of 8 over 1 squared, plus 8 over 3 squared, plus 8 over 5 squared, and so on. Okay, so what I'm going to do now is show you that this actually is true in a more easy to understand way. I'm going to start evaluating this series. So this is my new function g of y, and y basically is that I've just taken as my top limit. So basically, this is basically the summation of my terms. So this is basically a series of however many terms. So when y equals 0, this just represents one term of my infinite series. So you can see here I've got all my terms here. So I've evaluated it at y equals 0, which is just one term. You get 2.82843. Y equals 1, a little bit closer. And you can see, as you add more and more terms in, it gets closer and closer to pi. And I can only go as far as the 7,000th term, because my computer can't deal with anything more than that. But at the 7,000th term, you get g of y equals 3.14159. And that's to 1, 2, 3, 4, 5, 6 figures. And pi is 3.14159 to 6 significant figures. So I'm only 0.00004 out. So after the 7,000th term, you're pretty close to pi. Okay, to conclude this video, I'd like to show you another pi series. And this one's quite a lot simpler than the one I showed you. Pi equals the square root of n equals 1 to infinity of 6 over n squared. You can prove this one using the same method. And I'll give you a hint about how to do that. Let your f of x equal x squared instead of x. This top thing is x squared instead of x. And if you follow this through, you will get another series for pi, and it will turn out that if you do some rearrangement, you get this. And actually, the trick to working out this one will also involve the bn's, the sine series. So you might have to evaluate at another point other than 0, and obviously the point to pick is to evaluate to pi and see what happens. So that's basically how you do it. You might have to change your period to something else, but this is the way to go about trying to prove this. In fact, there are actually there's a lot more than just these two as well. You can use this method to generate as many different types of infinite series of pi as you like, which is a fairly interesting thing to do if you're interested.